We grow up with Jupiter in our heads as the final answer to planetary size. It is the giant in children's books, the striped sovereign of the solar system, the world so large that all the other planets seem to arrange themselves around its confidence. And that picture feels stable, right up until you learn that out in the dark, around another star, there is a confirmed planet, so swollen that Jupiter stops looking like the limit and starts looking like a familiar reference point we have already outgrown. The deeper shock is not that something bigger exists. It is that this larger world is not more solid, not more powerful in the way we instinctively imagine, and not even built on the kind of common sense our bodies were trained to trust. If you like long journeys into realities that get stranger the closer you look, stay with me. This one begins with the biggest planet we thought we understood, and ends with the unsettling possibility that we never really understood what big meant in the first place. So with that in mind, let's start with something familiar. Jupiter deserves its reputation. Even now, after centuries of observation and decades of spacecraft data, it still feels excessive. You can line up every other planet in our solar system, and Jupiter remains the heavyweight presence in the room. Its diameter is roughly 11 times Earth's. Its mass is more than twice that of all the other planets combined. It carries storms large enough to swallow worlds, magnetic forces vast enough to trap deadly radiation, and a retinue of moons that almost makes it feel like a miniature solar system of its own. When we say giant planet, we are usually speaking Jupiter's language, even if we do not realize it. That is why the first number attached to HAT-P-67b feels wrong before it feels interesting. Its radius is listed at a little over twice Jupiter's, not twice Earth's, not twice Neptune's, twice Jupiter's. That kind of number is hard to let into the mind all at once, because Jupiter already occupies the oversized corner of our imagination. It is like being told that the biggest cathedral in the city has a shadow so large that it makes the mountain behind it look smaller than you remembered. Your first instinct is not curiosity, it is resistance. Something in you wants to ask whether there has been a mistake, whether the measurement is uncertain, whether the word planet is being stretched beyond usefulness. That hesitation is healthy. Astronomy is full of claims that become less dramatic when you look closely. But this one becomes more dramatic because the number is not the end of the story. It is the trap door. The reason HAT-P-67b matters is not merely that it is wider than Jupiter by an almost absurd amount. The reason it matters is that it breaks the simple logic we carry around from daily life. In ordinary experience, larger things are usually built from more stuff. A bigger truck weighs more than a small one. A larger stone is heavier than a pebble. A house twice the size of another house does not usually turn out to be made mostly of emptiness and warm air. Planets do not always honour that intuition. HAT-P-67b is thought to have only a fraction of Jupiter's mass. Not a little less, far less. Imagine a world with a silhouette that can dwarf the giant of our own system, while containing much less of the actual material that gives a planet heft. That is the first real turn in this story. The largest planet we have found by physical size is not a bulked-up version of Jupiter. It is more like an overinflated giant, a world stretched outward into a shape that almost feels temporary. And once that lands, the title changes meaning, because now we are no longer asking, what planet is biggest? We are asking, what kind of world can become that large without collapsing back into something denser, tighter, and more familiar? To answer that, we need to pause on something easy to overlook. We have never flown past HAT-P-67b. We do not have a clear photograph of it hanging against the black, the way we do with Jupiter or Saturn. This world first entered human knowledge as a pattern in starlight. That matters because it tells you something about the delicacy of the evidence and the power of the method. A distant star dims by a tiny amount regularly as something passes in front of it. From the depth of that dip, from the rhythm of the orbit, from the way the star itself wobbles under the pull of an unseen companion, we begin to infer a world. That is how many of the strangest planets in the universe first announce themselves. Not with an image, but with a subtraction. A little less light, A repeated shadow. A signal small enough to hide inside noise unless you know how to listen. There is something almost intimate about that. We are not standing above these systems like gods reading labels. We are sitting at a distance that the human mind cannot naturally hold, watching stars flicker, and from those flickers, reconstructing entire worlds. Radius, mass, orbital period, density, atmospheric hints, temperature ranges, likely structure. The record holder does not arrive as a postcard. It arrives as a deduction so precise that, once complete, it becomes hard to imagine it had ever been invisible. And it was invisible for almost all of human history. That is worth feeling for a moment. For thousands of years, Jupiter was not just our largest planet. It was one of the only kinds of giant world we knew existed at all. A huge, striped body hanging in our own sky, close enough for telescopes, bright enough for awe, distant enough to remain a little untouchable. Then, in a span so short it barely counts as time by cosmic standards, we learn that the galaxy is crowded with worlds stranger than the ones that raised our intuition. Some skim their stars in days. Some are hotter than molten rock should allow. Some rain metal. Some are crushed into densities that make ordinary matter feel soft. And some, like HAT-P-67b, swell outward into dimensions that force us to stop treating planet as a tidy idea. If you could approach a world like that, the weirdness would begin before you ever got near the clouds. Jupiter, immense as it is, still belongs to a mental category we can picture. It is compact in the emotional sense, heavy, pressurized, dense enough in the way a giant gas world can be, to feel coherent. HAT-P-67b pushes at the edge of that feeling. A radius over twice Jupiter's means a volume so much greater that the mind has to fight not to flatten it into just another number. This is not a slightly enlarged Jupiter drifting through a quiet orbit. This is a planet with the physical breadth of a giant fantasy, yet with so little average density that the whole object begins to feel less like a boulder and more like an enormous layer of heated atmosphere holding a shape against the dark. A world can be huge and insubstantial at the same time. That is not how Earth teaches you to think. It is how the universe teaches you to unlearn. And the more closely we look at giant planets, the stranger that lesson becomes. Because HAT-P-67b is not simply an outlier sitting alone at the far edge of possibility. It belongs to a class of worlds that have been trying for years now to warn us that Jupiter was never the ceiling we thought it was, and that the physics of bigness changes the moment heat, gas, and gravity start pulling in different directions. Jupiter feels stable because our relationship with it is stable. We have watched it long enough that its immensity has become almost domestic. Even its violence has turned familiar. The great red spot, the belts and zones, the moons crossing its face, the patient turning of its storms across centuries of sketches and photographs. We know it as a giant, but also as a giant that seems to know how to remain itself. That quiet confidence is part of why it became our standard. The worlds beyond it do not always offer the same comfort. A giant planet close to its star lives under conditions that would dismantle our ordinary language for weather, season, and day. HAT-P-67b circles its star in less than 5 Earth days. Think about what that means in human time. Before you have fully settled into the rhythm of a week, that world has completed a year. Before a city has moved from Monday's first traffic to Friday's tired evening, this planet has gone all the way around its sun. That pace tells you immediately that it is not living in the distant, cold outer reaches, where we instinctively place giant planets. It is tucked in close, held near its star, in an orbit that would feel almost reckless if planets were creatures capable of fear. And close changes everything. In our solar system, the gas giants live far out where sunlight is thinned by distance. Jupiter receives only a small fraction of the solar energy that falls on Earth. Even there it remains enormous, because it formed out in the colder regions of the young solar system, where giant planets could gather and hold thick envelopes of hydrogen and helium. That is the model people often carry without realizing it. Giant planets belong far from the star. Big means distant, Massive means cold enough to keep its gases. The architecture of our system teaches that lesson so strongly that when we encounter a giant world pressed almost against its own star, it feels like a category error. But the galaxy does not care what our local arrangement taught us. Hot Jupiters were one of the first great shocks of exoplanet astronomy. Huge gas giants, scorched by stars they orbit at astonishingly close range, rushing around in days instead of years. They were not what many scientists expected to find first, and not what the public expected to hear about when people started talking seriously about planets around other suns. Yet they kept appearing again and again, because they are among the easiest giant exoplanets to detect. Their large size makes them cast noticeable shadows during transits. Their strong gravitational pull makes their stars wobble in measurable ways. They are loud in the data, and some of them are physically swollen. That swelling is one of the most important ideas in this entire story. If you stop too early, largest planet sounds like a record book category, a contest in diameter. But the reality is more revealing than that. Giant worlds made mostly of hydrogen and helium do not just keep expanding forever as they gain mass. There is a regime in which extra weight presses inwards so effectively that the planet does not become much larger at all. In some cases, it can even become smaller. The material is compressible. Gravity does not politely step aside just because more matter has arrived. It squeezes harder. So once a gas giant reaches roughly Jupiter-like scale, the path to becoming truly enormous in radius is not simply to become more massive. That route stops working the way common sense expects. The route is heat. Not heat alone, and not in any simple cartoon form, but heat is at the centre of the mystery. A planet parked close to a hot star receives an extraordinary flood of energy. Its outer layers can become intensely heated. Its atmosphere can puff outward. Internal processes may trap or redistribute energy in ways that keep the planet larger than simpler models predict. The details are still being worked out in many cases, and astronomers are careful about pretending the problem is fully solved. But the broad picture is clear enough to feel. Some giant planets are not large because they are overwhelmingly massive. They are large because they are hot, inflated, and held in a kind of physical tension. A tug of war is a useful way to picture it. Gravity is always trying to pull the planet inward, to compress it into something tighter and more compact. The heat pouring in from the star, along with heat moving through the interior, helps prop the outer layers outward. Neither side fully wins. What we see is the shape of that struggle. And in HAT-P-67b, the struggle appears to be extreme. Its average density is astonishingly low. This is the point where many people reach for analogies, and most of them feel either too cute or too blunt. But we do need something felt rather than abstract. Jupiter, huge as it is, still carries itself like a giant body. HAT-P-67b begins to sound more like a world made of thinness. Not empty, not unreal, but diffuse, spread out. Its size is being carried by a vast, bloated envelope of gas that does not contain nearly as much matter as its dimensions would tempt you to assume. It is a little like seeing a colossal structure from a distance, and then learning that much of what gives it shape is not stone, but heated fabric held under tension. That image is imperfect, every image is, but the point lands. This is not giant in the way a mountain is giant. It is giant in the way an atmosphere can be giant. That difference matters because it changes the emotional character of the planet. Jupiter feels imposing. HAT-P-67b feels precarious. The same data that make it impressive also make it uneasy. A very low-density world under intense irradiation does not read like a monument. It reads like something pushed outward toward a limit. That is why these planets are so scientifically valuable. They expose the physics that ordinary giant planets hide. When a world becomes this inflated, it lets us see how stellar energy, atmospheric structure, internal heat transport, and gravity interact under extreme conditions. The record is not just spectacle, it is diagnostic. It tells us where our models of giant planets still need refinement, and where nature has found ways to create states of matter and structure that sit right at the edge of expectation. You can feel the educational beauty in that. The strangest worlds are not distractions from the rule. They are often the best places to see the rule itself. And when we say HAT-P-67b is one of the largest known planets by radius, the phrase by radius carries more weight than it seems to. Radius is a clean measurement in one sense, but it can also deceive intuition. Twice the radius is not twice the planet in the way people casually imagine. Volume rises dramatically. Presence rises dramatically. Silhouette rises dramatically. Yet mass may not follow in step. That mismatch is the centre of the wonder here. The planet looks like it should dominate Jupiter by every measure. It does not. Size has split apart from heft. Once that happens, you start noticing how often our language fuses things that reality keeps separate. Bigger, heavier, stronger, denser, more stable, more important. We treat those as cousins because most ordinary objects encourage us to. But stars, planets, and substellar objects are under no obligation to preserve the family resemblance of our adjectives. A body can be larger without being heavier. It can be heavier without being wider. It can be more impressive to the eye while being less secure in its own structure. It can look like triumph and actually be stress. That last idea is worth holding on to because it leads us toward the next break in intuition. If being the largest known giant planet by physical size does not mean being the most massive, then what about the truly heavy objects that sit near the boundary between planet and failed star? What happens there is even stranger, because that is where the universe stops merely bending our common sense and begins folding it back on itself. The moment we follow mass instead of width, Jupiter changes character again. It stops being just the giant we know and starts becoming a threshold. That is one of the deepest hidden facts in planetary science. Jupiter is not merely the largest planet in our own system by a comfortable margin. It sits near a strange natural plateau, a realm where bodies made mostly of hydrogen and helium do not respond to added matter the way rocks, buildings, and everyday objects do. Add more weight, and past a point, you do not get a dramatically wider world, you get stronger compression. This is where the universe grows quiet and ruthless at the same time. If you kept piling matter onto a Jupiter-like body, intuition would suggest a sequence of ever larger giants. A bigger Jupiter, then a much bigger Jupiter, then a colossal one, and so on until the word planet finally gives up. But giant gaseous bodies are not inflated balloons that simply stretch in proportion to what you feed them. Their interiors live under pressure so severe that matter begins to behave in ways that feel alien to common sense. The gas is squeezed. Electrons are crowded. The whole object resists expansion. A body can gain enormous mass without gaining much visible breadth at all. That is not a small correction to intuition. It is a reversal. Some brown dwarfs, objects heavier than planets but too light to become full stars, can carry dozens of times Jupiter's mass while remaining roughly Jupiter-sized. Think about how disorienting that is. A world-like body can become vastly heavier without becoming vastly larger. Imagine lifting a pillow and finding that every extra layer added to it somehow makes it denser rather than broader, tighter rather than puffier. It is the opposite of how abundance usually feels. The result is that Jupiter stops looking like one giant among many possible larger giants. It begins to look like a clue. There is a reason so many bodies in that broader family cluster around similar sizes. The laws shaping hydrogen-rich worlds funnel them toward a limited range of radii, even while mass varies wildly. That means a planet like HAT-P-67b is not extraordinary because it is on the same simple ladder as Jupiter and just happened to climb higher. It is extraordinary because it seems to have escaped the ladder altogether through inflation. That is a very different kind of record. It is the difference between being the strongest athlete in a normal competition and being the person who discovered a way to alter the event itself. When you see it that way, the title stops sounding like a boast and starts sounding like a warning. The largest planet we have found is not proof that the universe makes steadily bigger and grander versions of familiar things. It is evidence that familiar things can be physically distorted into states that feel almost implausible. HAT-P-67b is not the natural next step after Jupiter. It is what happens when a giant world is heated, stressed, and expanded beyond the range our solar system taught us to expect. And that is why brown dwarfs matter to this story, even though they are not planets in the same straightforward sense. They occupy the neighbouring territory where language gets uneasy. Too massive to fit comfortably within the image of a planet, too small to ignite hydrogen fusion like true stars. Failed star is the old phrase people like to use, though it can be misleading because it makes these objects sound incomplete rather than distinct. In reality, they are their own class of things. But what matters for us is the size comparison. Some are immensely massive, yet not immensely larger in radius than Jupiter. That forces an uncomfortable admission. Physical size alone is not a simple ladder from planet to star. Nature does not arrange these bodies in the smooth, visual procession our diagrams tempt us to imagine. Categories begin to blur at the edges, and human beings do not love blurred edges. We like lines. We like words that close around objects cleanly. Planet, star, moon, gas giant, brown dwarf. We understand that these are useful terms, but somewhere underneath that practical knowledge sits a childlike desire for them to be neat, complete, and permanent. Astronomy keeps disappointing that desire in the best possible way. It keeps showing us that the universe is not messy because we are ignorant. It is messy because reality contains transitional states, threshold behaviours, and structures that only look simple from far away. HAT-P-67b lives in that discomfort. It is clearly treated as a planet, and rightly so in the current framework, but it also helps expose how unstable our mental categories can become once we leave the safe neighbourhood of the solar system. It is so physically bloated that the word giant stops feeling sufficient. Yet it is not giant by piling on overwhelming mass. It is giant by being heated and stretched into a swollen state. You could say that Jupiter teaches us what a giant planet looks like when gravity has won with confidence, while HAT-P-67b shows us what a giant planet looks like when gravity is still winning in the long run, but has been forced into a tense compromise in the present. That compromise is part of what makes the planet emotionally haunting. There is something almost tragic in a world whose record size may be tied to stress rather than security. We are used to thinking of records as crowns, fastest, biggest, brightest, strongest. Yet some records are signs of strain. The tallest wave in a storm is not the sea at peace. The hottest day in a city is not the climate at equilibrium. The most swollen giant planet may not be a settled masterpiece of planetary architecture. It may be a body in a temporary physical condition that cannot last forever. That idea brings us closer to the real atmosphere of these worlds. And atmosphere here means more than chemistry, it means mood. Jupiter feels ancient and composed. HAT-P-67b feels like a world caught in the act of being altered. Even if we never see it directly as more than changing starlight and model-based reconstructions, the physical story has texture, a close orbit, intense stellar energy, an enormous radius, a strikingly low density. The image that forms is not one of compact authority. It is one of expansion under pressure. And if that expansion is real, then there is a harder question waiting behind it. How long can a planet remain like this? That question matters because there is no guarantee that the conditions producing such a bloated radius are stable across cosmic time. A world can exist in a state that is spectacular to measure, and yet fleeting on the scale of planetary history. That possibility changes how we emotionally rank what we are seeing. The largest known giant planet by radius might not be the end point of a design. It could be a caught moment, a phase in which heat, orbit, and atmospheric structure have temporarily pushed a world to one of the most extreme silhouettes a planet can hold before some slower process begins to undo it. And once you allow time into the picture, these swollen worlds become less like kings and more like witnesses to a struggle that is still unfolding. Time changes the feeling of every object in space. A mountain seems solid until you remember erosion. A coastline seems permanent until you measure it against centuries. A star seems eternal until you learn how quickly it burns through one phase and passes into another. The same is true here. HAT-P-67b is easiest to misunderstand if we imagine it as a static monument, a giant thing that simply exists in the form we now infer. But the more we understand about highly inflated hot giants, the harder that static picture becomes to maintain. A planet living this close to its star is not merely warm, it is under constant assault from energy. The upper atmosphere is heated, stretched, and in some cases driven outward. Radiation strips at the planet's outer layers. The star's gravity and the planet's own gravity interact across a very small orbital distance. Tides matter, heat matters, escape matters. A giant world in such a tight orbit is not resting, it is enduring. That is one reason the newest work on HAT-P-67b feels so compelling. The picture emerging is not just of a very large planet, but of a very large planet that may be losing itself. Not all of it at once, not in some melodramatic, cinematic unravelling, but through processes that are slow by human standards and decisive by planetary ones. Gas can escape, outer layers can be peeled away over time. Orbital evolution can change the balance further. A swollen world can become a shedding world. That possibility gives the planet a very different emotional shape. When we hear largest, we tend to imagine supremacy, something that won, something that stands above its category in a stable and almost triumphant way. But there are records that belong to edge states rather than champions. A fever is a temperature record for a body in distress. A market peak can be a record of instability rather than health. The most physically inflated giant planet may belong to that same family of truths. It may not be the most complete expression of giant planet design. It may be one of the most strained. This is where the story stops being just a scale story and becomes a reality story. Because the universe is full of things that look strongest at the moment they are being pushed hardest. If HAT-P-67b is indeed experiencing significant atmospheric loss, then its vast radius is not only a description of what it is a clue to what is happening to it. The planet's outer layers may be so expanded that they are easier for the star to erode, and that is an eerie idea, because it means the feature that makes the planet famous may be entangled with the process that prevents it from staying this way forever. The record could be part wound. There is something quietly moving about that. We are used to thinking of the cosmos as indifferent, but not often as vulnerable. A giant planet sounds durable by default. Yet here is a world whose dimensions suggest excess, while its underlying physics suggest exposure. It is enormous, and that very enormity may be tied to a delicate balance that can fail. You can feel the tension more clearly if you imagine approaching the system not as a tourist, but as a patient observer. The star is hotter and more luminous than the sun. The planet whips around it in a path so tight that distance itself has become a kind of pressure. The day side would be subjected to brutal irradiation. The atmosphere would not sit politely in place as though arranged for our convenience. Heat would move, gases would expand, and the upper layers would become part of an ongoing negotiation between being held and being lost. In that light, planet as weather all the way down does not sound like exaggeration, so much as a reminder that our usual image of a world often smuggles in the wrong assumptions. We picture a surface. We picture a place where solidity begins. But for a hot giant, especially an inflated one, the meaningful structure is not a hard shell under a thin sky. The structure is the sky, deepening and thickening through pressure into something more continuous than our daily experience prepares us for. The object is real. The gravity is real. The mass is real. Yet the way its size is expressed is atmospheric. That is part of why the density figure lands so hard. Numbers like that are not memorable because people enjoy decimals. They are memorable because they expose a mismatch between appearance and substance. A planet can command an enormous volume while remaining astonishingly diffuse. It can carry a shadow of grandeur that exceeds its actual load of matter by a breathtaking margin. The silhouette is not lying, but it is not telling the whole truth either. And what holds for a single planet begins to widen into a lesson about astronomy itself. Again and again, The universe offers us cases where the thing easiest to picture is not the thing most important to understand. Brightness is not always energy in the way it seems. Size is not always mass in the way it seems. Motion is not always distance in the way it seems. The visual intuition we inherited from living among rocks, trees, bodies, and weather on Earth is powerful, but it is provincial. It was trained locally. Exoplanets expose that localness with unusual cruelty. Jupiter already challenged our ancestors by being a world without a solid face we could ever stand on, a giant that was not a star, a wandering light that moved unlike the fixed constellations. Yet even Jupiter, for all its strangeness, fits within a certain calmness once you know it well. HAT-P-67b belongs to a different emotional climate. It is a reminder that giant planets can be not only huge, but unstable in their hugeness, not only distant, but dynamically stressed, not only difficult to imagine, but difficult to classify in any satisfying emotional way. You cannot simply look at its radius and feel that you know what sort of thing it is. That discomfort is productive. It is doing work on the mind, because what begins as surprise about one record holder gradually becomes distrust of a larger assumption, the belief that the biggest objects are also the most self-explanatory. In ordinary life, very large things can be simpler than medium ones. A wall is just a bigger board. A whale is just a larger animal than a fox, at least from the outside. But in astrophysics, extreme size often does the opposite. It strips away intuitive shortcuts. It reveals new regimes of pressure, heat, chemistry, and time. The most oversized planets are often not easy cases. They are where the clean rules begin to fray. And once you accept that, another giant enters the frame in a new way. Not to steal the story from HAT-P-67b, but to prove that this world is not a freak accident with no larger meaning. There are other swollen worlds, other hot giants that carry absurdly large radii for their mass, other cases where the universe seems almost to be sketching the outline of a giant planet and then filling it with less matter than your instincts would permit. One of the most famous is WASP-17b, and its existence matters because it shows that HAT-P-67b is part of a pattern. A rare pattern, yes, but a pattern. And patterns are where astonishment becomes understanding. WASP-17b does not replace HAT-P-67b in this story. It strengthens it. One inflated giant can feel like a curiosity, the astronomical equivalent of a bizarre coin minting error that tells you more about chance than about the system around it. But when you find multiple worlds with the same broad pattern, enormous radii, comparatively low masses, close orbits, severe stellar heating, the strangeness starts to organize itself. The record holder remains special, yet no longer isolated. A class of planets begins to emerge, and with it, a more difficult truth. Nature is not improvising wildly. It is exploring a real physical regime that our own solar system simply does not display. WASP-17b is one of the clearest examples of that regime. It is another hot giant with an extraordinary physical scale compared with its mass, another world whose volume feels out of proportion to the amount of material holding it together. It helped shape the modern sense that some giant planets are not merely large but inflated. Their atmospheres expanded to sizes that would have seemed absurd if Jupiter were still our only guide. That comparison matters because it keeps HAT-P-67b from becoming a novelty act. We are not looking at one impossible world. We are looking at a family resemblance among planets under similar pressure. And family resemblance changes the kind of question we ask. At the beginning, the question is emotional and almost childlike. How can something bigger than Jupiter exist? Once the pattern becomes visible, the question becomes more mature and more interesting. Under what conditions do giant planets swell this way, and why do some respond to those conditions more extremely than others? That is where the science becomes less like a list of records and more like a living argument. The simplest version is that hot giants are exposed to stellar amounts of stellar energy, and this heating affects their outer layers, sometimes enough to enlarge the planet well beyond what a colder gas giant of similar mass would be expected to maintain. But the word heating can hide complexity. A planet does not just sit under a lamp and expand like a toy left in the sun. Energy arrives, is absorbed at different depths, is redistributed by atmospheric motion, may be converted into winds, may leak away, may be trapped, may stir deeper processes, may interact with magnetic effects, and may reach into the interior more effectively in some worlds than in others. The observed inflation problem has been with us long enough to show that there is no single neat sentence that closes it. That uncertainty is part of the credibility here, not a weakness. It tells you that the planets are real enough to break the models. In astronomy, some of the best questions arise when the object refuses to be as simple as the equations first hoped it would be. HAT-P-67b is powerful, not because it sits comfortably inside what we already know, but because it puts pressure on that knowledge. A world this puffed up is not just another entry in a catalogue. It is a demand for better planetary physics. And because the explanation remains incomplete at the edges, the planet keeps its mystery without losing its legitimacy. We know enough to say that intense stellar irradiation matters. We know enough to say that these close-in giants are physically different from Jupiter in more than just location. We know enough to say that low density, large radius and tight orbit belong together in a meaningful way. What remains under active discussion is exactly how the incoming energy, internal structure, atmospheric circulation, and possible additional heating mechanisms combine to produce the most extreme cases. That is the right kind of unknown. It pushes the story forward. It also rescues the script from a cheap temptation, which would be to treat the planet as a cartoon monster. The real wonder is subtler than that. HAT-P-67b is not impressive because it breaks nature. It is impressive because it obeys nature so fully that we are forced to notice laws we would otherwise miss. Its enormity is not magic. It is physics under unusual conditions. Once you understand that, the planet becomes even stranger, not less, because the strangeness is no longer decorative. It is lawful. You can feel that lawfulness by going back to Jupiter one more time. Jupiter is huge, but it is also relatively compact for what it is. Its mass gives it a gravity that compresses its material inward. Its distance from the Sun spares it the kind of intense irradiation that bloats hot giants. It radiates more heat than it receives from sunlight, carrying an internal energy history of its own, but not in the same punishing environment as a hot Jupiter parked extremely close to a bright star. So Jupiter's size expresses one balance of forces. HAT-P-67b expresses another. Both are giant planets. They do not mean giant in the same way. That is the kind of sentence that can quietly rearrange your sense of the universe. The category remains useful, yet the lived physics inside it can diverge enormously. It is a reminder that labels are doors, not destinations. Gas giant gets you into the room. It does not tell you what every world inside the room has endured. And endure is the right word here, because close orbits are not peaceful places for giant planets. These systems ask their planets to survive heat, tides, and long exposure to stellar energy on scales that reshape atmospheric structure. A swollen planet can become more vulnerable to loss from its upper layers. In some cases, the whole configuration starts to feel less like a final stable arrangement and more like a temporary chapter in an ongoing transformation. That temporal aspect is easy to miss, because planets seem timeless from a human perspective. We name them as though they are static objects, and on human timescales, that is mostly reasonable. But a hot, inflated giant may be changing in ways that matter profoundly over tens or hundreds of millions of years. That is a long time to us, beyond every empire and every language we know. Yet in planetary history, it can be the span of an important phase rather than the whole story. A world can spend a while in an expanded, vulnerable condition and later become something else through mass loss, contraction, or orbital evolution. So what if the largest looking planet is not the final form of a giant planet, but a caught moment in its life? That question adds emotional depth to the record. We are not merely staring at the biggest silhouette among confirmed giants. We may be seeing a world during one of the most revealing and unstable stretches of its existence. the title begins to widen again. Makes Jupiter look small is still true in one physical sense, but the deeper payoff is that it makes Jupiter look calm. It makes Jupiter look settled. It makes Jupiter look like one answer among many, rather than the giant template against which all others should be judged. And once Jupiter stops being the template, the whole architecture of our expectations starts to loosen. If a giant planet can be this wide without being overwhelmingly massive, this inflated without being imaginary, this real while still partly unresolved in mechanism, then perhaps the larger lesson is not about one exoplanet at all. Perhaps it is about the danger of trusting any category too quickly, when reality has only just begun to speak. Because the more worlds we discover, the more obvious it becomes that our first planetary vocabulary was written from a sample size of one system. The galaxy was always free to answer in accents we had never heard. For a long time, our sense of what a planet could be was shaped by 8 examples and a few demotions, arguments, and refinements around the edges. That was enough to build textbooks, enough to build childhood intuition, enough to make the solar system feel like a complete introduction. But it was not enough to reveal the full grammar of planetary reality. It was a local dialect, useful, beautiful, and badly incomplete. Once exoplanet catalogues began to fill, that incompleteness became impossible to ignore. The first shock was numerical. There were not a few worlds out there. There were many. Then the second shock arrived, which was more intimate. They were not arranged according to the expectations our home system had trained into us. Giant planets close to stars, orbits so tight they seemed almost unstable by instinct alone, densities too low or too high for comfort, compositions inferred from starlight that made the imagination stumble. Every new class of exoplanet was a little humiliation for common sense, and also a gift. The giant inflated worlds sit at the centre of that gift because they force us to revise not just one fact, but a whole cluster of linked assumptions. We tend to bundle size, mass, stability, and importance together because that bundle works well enough on Earth. If something is larger, it often feels more substantial. If it is more substantial, it often feels more permanent. If it is more permanent, it feels more authoritative. HAT-P-67b peels those assumptions apart one by one. It is larger in radius than Jupiter. It is not correspondingly more massive. Its size may be tied to a stressed physical state rather than a secure one, and its existence reminds us that the universe does not rank objects according to the emotional logic of our adjectives. That is why this story keeps becoming larger than the title, while still paying the title off more deeply. Because by this point, largest no longer means what it meant at the start. At first it meant broadest silhouette, a giant shadow crossing a distant star, a radius that exceeds the radius of Jupiter by enough to make the mind jolt awake. Then it came to mean inflated scale, the kind of size produced not by overwhelming mass, but by a world spread outward under extreme heating. Now it begins to mean something stranger still, a maximum in physical appearance that may only exist because the planet has been pushed into a vulnerable regime. The record is still real, but the reality of the record has become more layered, more conditional, and far more revealing. There is a quiet maturity in that shift. Early curiosity asks, what is the biggest thing? Deeper curiosity asks, what forces allow that thing to look the way it does? The deepest version asks, what does that force us to admit about the limits of our intuition? And the answer, here, is not flattering. Human intuition is excellent within the scale of ordinary life. It can read balance from posture, weight from motion, weather from a sky, age from a face, danger from sound. But it was not trained for hydrogen under enormous pressure, or for worlds so close to stars that a year lasts less than a work week, or for objects whose visual scale can be dramatically out of step with their actual mass. It was not trained for bodies that gain weight without much gain in radius, or for bodies that become huge because stellar heat and gravity are locked in a prolonged argument. We had to invent new senses for that, not biological senses, instrumental ones, mathematical ones, statistical ones, telescopes that do not just enlarge, but detect tiny losses of starlight. Spectrographs that notice a star rocking slightly under the pull of an unseen companion. Models that convert those faint changes into orbit, size, mass, density, likely temperature, and atmospheric behavior. When people say astronomy is about looking outward, that is true, but incomplete. It is also about extending the mind beyond the scale conditions under which intuition evolved. That extension is one of the most astonishing things human beings do. We take a dimming star and infer a giant planet. We take repeated measurements across years and turn them into a world with a name, an orbit, a probable structure, and a place in the broader map of planetary behavior. We do not simply gaze and wonder. We gaze, measure, compare, argue, refine, and eventually come away able to say, with real confidence, that there exists a world so expanded that Jupiter, our old giant, is no longer the outer wall of our imagination. There is something deeply moving in that kind of precision, not because it flatters us, but because it doesn't. The measurements do not tell us that we were close enough all along. They tell us we were provincial, and that careful attention can rescue us from that provincialism. They tell us the universe is not obligated to feel natural before it is understood. That becomes especially clear when we return to the boundary with brown dwarfs. It would be easy to drag them into this narrative only as a bigger, heavier comparison, but their real function is more philosophical than competitive. They reveal a neighbouring regime in which mass can soar while radius hardly changes. They show us that there is no smooth emotional staircase from planet to star. Instead, there are thresholds, plateaus, and category edges where physical behaviour shifts. Jupiter sits near one of those thresholds. HAT-P-67b departs from it through inflation. Brown dwarfs lean the other way into compression. The result is not a neat size hierarchy, but a landscape. And landscapes are harder to memorise than ladders. A ladder tells you where things rank. A landscape tells you where things belong, what pressures shape them, and how one region can differ dramatically from the next. That is what exoplanet science has been building for us. Not a longer list, but a wider terrain. In that terrain, some worlds cluster around Jupiter-like sizes across an enormous range of masses. Some worlds swell beyond that size because of heating and atmospheric inflation. Some move towards stellar behaviour without fully becoming stars. Once you see the terrain this way, the phrase largest planet becomes less like the name of a champion and more like a marker on a map of extreme conditions. That map is still incomplete, and it should stay incomplete in our minds if we want to remain honest. New observations refine radii, new catalogues shift how objects are grouped, better atmospheric data change the details of our models. Even Jupiter itself, the benchmark we treat as ancient and settled, is still being measured more carefully, its shape and size described with increasing precision as missions and analyses improve. That should not make the story feel uncertain in a weak sense. It should make it feel alive. Astronomy is not a museum of fixed labels. It is an unfolding discipline of correction, and correction is part of wonder. The mature form of awe is not gasping at whatever sounds largest. It is learning that reality resists your first summary, then feeling grateful that it did. So HAT-P-67b remains where it began, and yet not at all where it began. A confirmed giant exoplanet with a radius over twice Jupiter's, one of the physically largest known planets by that measure. A bloated, intensely irradiated, low-density world in a tight orbit around a hotter star. Likely not a simple, stable endpoint, but a body in a stressed condition that may be shedding atmosphere and moving through a phase that cannot last forever. That is already enough to justify the title. But it has also become clear that the title is merely the doorway, because a world like this does not just make Jupiter look small. It makes our old confidence look small too. And that shrinking of confidence is not a loss. It is one of the best things that can happen to the mind. There is a special kind of relief in realizing that reality is under no duty to fit the scale models we built from childhood posters and classroom diagrams. We were not wrong to begin with Jupiter, we were simply early. Early humans looked up and saw wandering lights among fixed stars. Later generations learned that some of those wandering lights were worlds. Much later, we learned that one of them, Jupiter, was not just a bright moving point, but a giant sphere with bands, storms, moons, and a mass so dominant that it shaped the structure of the solar system around it. And now, in another small step that feels enormous once it settles in, we have learned that even Jupiter is provincial. Monumental, yes. Foundational, yes, but still provincial. A local expression of giant planet physics, not the final word. That change in perspective is worth slowing down for, because it is easy to treat it as just another scientific update. Bigger planet found, catalogue expanded, move on. But that flattening misses the emotional texture of discovery. The old map was not just missing a point, it was missing an entire style of world. A world like HAT-P-67b would have felt almost irresponsible to invent in an earlier era. If you had written it into fiction before the exoplanet revolution, a giant planet more than twice Jupiter's radius, with far less mass, bloated under intense stellar heating, racing around its star in less than 5 days, so diffuse that its size feels almost atmospheric, it might have sounded like excess for its own sake. Too decorative, too eager to be strange. Yet that is precisely why reality is better than invention. It has no need to be plausible to us before becoming true. The truth arrives anyway. And when it does, it rarely arrives alone. Once a few inflated hot giants were established, they began to change how astronomers looked at every new detection. A big radius no longer meant simply more giant. It meant check the mass. It meant look at the orbit. It meant how irradiated is the planet. It meant, what do the density and stellar environment imply? In other words, discovery did what the best discoveries do. It retrained the questions. That is how a field matures. Not by collecting facts until the shelves are full, but by becoming harder to fool. Before exoplanets, the phrase gas giant carried a relatively narrow emotional range. It suggested something like Jupiter or Saturn. Large, majestic, far from the star, massive enough to dominate a neighbourhood, calm enough from a distance to seem eternal. After exoplanets, the phrase stretched. Now it had to include worlds skimming close to their stars, worlds heated into inflated states, worlds tidally locked, worlds whose atmospheres may be escaping, worlds whose observable properties force modelers to argue in finer detail. The category survived, but it lost its innocence. That loss is everywhere once you start noticing it. A giant planet no longer guarantees distance. A giant radius no longer guarantees giant mass. A larger object no longer guarantees a denser one. A more dramatic silhouette no longer guarantees a more stable world. The old bundle has come apart, and the mind has to build a new one from more disciplined pieces. This is one of the reasons the story remains calming even while it gets stranger. The deeper logic is not chaos, it is refinement. We are not discovering that the universe is random, we are discovering that it is more precise than our first metaphors allowed. A hot giant swells for reasons, a brown dwarf compresses for reasons. Jupiter sits near a size plateau for reasons. None of those reasons are obvious to untrained intuition, but once seen, they bring a harder, cleaner beauty into view. Pressure, heat, composition, distance, time. These are not poetic substitutes for understanding. They are the actual forces writing the worlds. If you imagine standing very far away and trying to sort giant bodies by appearance alone, you might be misled almost immediately. One could be physically broader, but far lighter. Another could be enormously heavier, while looking only modestly larger. Another could be midway through a period of atmospheric loss that makes its current state a temporary exaggeration of itself. The visual hierarchy would not be the physical hierarchy. That is one of the central shocks hidden inside this subject. The biggest looking object is not always the deepest object in terms of mass, and the deepest object is not always the most visually expansive. There is a human lesson tucked into that, and it is not sentimental. It is epistemic. Appearance is often a poor guide to structure when the governing physics changes. We know this in fragments on Earth. Clouds can look solid from below. Ice can conceal water. Steel beams can hide inside walls. A person can appear calm while under enormous strain. But astronomy stretches that lesson until it becomes almost metaphysical. The shape a world presents to us may be the outcome of invisible conflicts. A radius can be the surface trace of deeper balances we cannot see directly. HAT-P-67b is physically large, yes, but the more interesting statement is that its largeness is a symptom of a particular physical argument between gravity, heat, and atmospheric extension. And the argument is not fully over. That matters because it prevents the planet from becoming a frozen icon. It is one thing to marvel at a giant object. It is another to realize the object may be partway through changing. A planet in a stressed, inflated state invites a different kind of attention. Not admiration from below, but observation with tension. You begin to think in verbs rather than nouns. Heating, expanding, escaping, evolving. The world becomes not just something that is, but something that is happening. That shifting grammar is subtle and powerful. Nouns create stability, verbs create motion. Jupiter is easy to hold as a noun. HAT-P-67b resists that stillness. Even in still images, even in artist renderings, even in clean catalogue tables, it feels like a process caught in cross-section. And once you see a planet that way, you start revisiting old giants with new suspicion. Saturn's beauty becomes more structural. Jupiter's apparent solidity becomes more contingent. Brown dwarfs become less like oversized misfits and more like neighbouring solutions to the same broad problem of what hydrogen-rich bodies do under increasing mass and pressure. The landscape sharpens. The neat gallery gives way to a terrain of regimes. That terrain has edges we are still finding. Somewhere in the catalogue there may be worlds whose measured properties will yet force another revision. A new radius estimate, a new atmosphere detection, a new object whose mass sits awkwardly near a classification boundary. The point is not that every result will overturn what came before. Most will not. The point is that the map is still being drawn, and the shapes on it are already rich enough to humble the old confidence that giant planets were basically just Jupiter-like worlds in different neighbourhoods. They are not. Some are denser, some are hotter, some are stranger, some are stretched so far outward that planet begins to feel like an approximation for a structure whose outer identity is almost all atmosphere. Some, in the neighbouring brown dwarf territory, are so compressed that a casual observer would never guess how much mass has been hidden inside nearly the same radius. Bigness is no longer one thing. It is several different stories wearing the same adjective. That is why the title has continued to deepen instead of wearing out. The largest planet we have found makes Jupiter look small, yes, but by now, small is not the important word. The important word is look. Jupiter looks different after this journey. It looks less like the answer and more like the beginning of a question we had not yet learned how to ask. And once a question has changed, the night sky changes with it. The night sky does not visibly react when our understanding changes. Jupiter still rises with the same patient brightness. Stars still hold their distances. Constellations still preserve their old patterns, even after we have long since learned that they are not true groupings in space. Nothing up there rearranges itself to reward our insight. And yet the sky is never the same after a real correction enters the mind. One new fact, if it is deep enough, can alter the emotional geometry of everything around it. That is what worlds like HAT-P-67b do. They do not merely add a distant object to a growing archive. They modify the meaning of nearby objects. Jupiter becomes more interesting after you learn there are larger giants by radius that are far less massive. Brown dwarfs become more interesting after you learn that some of them hold vastly more mass without becoming dramatically wider. Even the idea of a star becomes more interesting, because the fate of a close-in, inflated giant depends so intimately on what kind of star it circles, how luminous that star is, how it evolves, and how much energy it pours into the planet's atmosphere, year after year after year. A giant planet is never only itself. It is always a relationship. That is another quiet correction hidden inside this subject. We often imagine planets as self-contained things, as if they could be understood the way we understand a statue in a museum, by walking around it conceptually and listing its properties: mass, radius, composition, orbital period, density. But a hot giant, especially an inflated one, resists that kind of isolation. Its size is not just something it owns, its size is partly a product of what is being done to it. The star matters, the orbit matters, the history matters, the current state of atmospheric escape may matter, even the future of the host star may matter. That makes the whole system feel more alive and also more uneasy. Because if the record-setting scale of such a planet is entangled with the influence of the star, then the planet's identity is inseparable from an environment that may continue to change. A world can become most visually extreme, not in spite of its circumstances, but because of them. The very conditions that make it unforgettable may also make it vulnerable. This is one reason the phrase hot Jupiter is both useful and slightly deceptive. It helps us quickly identify the broad category: a giant planet, roughly Jupiter-like in family, but orbiting very close to its star. Yet the label can also mislead by implying a simple before and after relationship, as though you took Jupiter, moved it inward, and that would be the whole story. In reality, close-in giants are not just Jupiter under stronger sunlight. Their atmospheres, internal heat flow, orbital histories, and long-term evolution can diverge in ways that make them physically and emotionally different kinds of worlds. Jupiter feels like gravity in command. HAT-P-67b feels like gravity sharing the room. That distinction may sound poetic, but it is deeply physical. Jupiter's size reflects a body compressed by its own mass into a state that, while still dynamic and astonishing, feels internally self-possessed. HAT-P-67b, by contrast, appears to occupy a regime where heat and irradiation have expanded the outer envelope so dramatically that the world's size announces tension rather than composure. You could almost say that Jupiter is an argument settled long ago, while HAT-P-67b is an argument still taking place. And because it is still taking place, the question of timescale becomes more intimate. Not because anyone expects to watch the planet visibly shrink in a human lifetime, but because scientific understanding changes when you stop treating the present state of an object as permanent by default. Some recent work suggests that the atmospheric loss on HAT-P-67b may be especially significant now, perhaps influenced by how its host star has evolved. If that picture holds, then we may be seeing the planet during a physically revealing era, rather than in some timeless average state. It is a little like encountering a coastline during rapid erosion. The shape is real, the beauty is real, but the shape also contains a history of forces acting on it, and a future in which it may not remain as it is. That thought does something important to the record. It lowers the voice. A title like this could easily be told at the volume of triumph: biggest, largest, more than Jupiter. But the truth we have uncovered does not really belong to triumph. It belongs to exposure, to physical extremity, to the fragile grandeur of a world stretched out under conditions that may be partly undoing it. The planet is still extraordinary, perhaps more extraordinary than the loud version of the story would have allowed. But its grandeur is quieter, stranger, less like dominance and more like imbalance held for a while against the dark. That quietness matters because it makes room for a different kind of awe. Not the awe of cartoon enormity, but the awe of lawful strangeness. The awe of learning that a giant world can become larger in radius, not by becoming overwhelmingly more massive, but by entering a regime where heat, atmospheric inflation, and stellar stress reshape what planet-sized can look like. The awe of realizing that beyond Jupiter, there is no single staircase of ever larger worlds, only different solutions to different physical pressures. The awe of seeing that a category we thought we understood was really just a doorway into multiple architectures of matter. And because the architecture is real, the imagination can finally relax into it. At the beginning of a story like this, the mind tenses because it expects exaggeration. A planet bigger than Jupiter by that much? Surely there is a trick. Surely largest is doing too much work. Surely the claim will dissolve into some technicality. But what actually happens is more satisfying. There is a technicality, yes, but technicality here does not weaken the wonder, it sharpens it. Largest by radius among confirmed giant exoplanets in the current observational landscape. Less massive than Jupiter, far more expanded, orbiting close to an F-type star. Extremely low density, likely inflated by intense irradiation and other coupled processes, possibly shedding atmosphere in a way that makes its present state especially revealing. None of that diminishes the title. It turns the title from a slogan into a lens. And through that lens, you start seeing other hidden inversions in astronomy more clearly. The brightest object is not always the hottest in the way you imagine. The nearest thing is not always the easiest to understand. The most massive body is not always the largest looking. The largest looking may not be the most secure. The categories that seem most obvious at a distance often become least obvious when measurements improve. That pattern is not a failure of science. It is science working. It is what happens when the universe is allowed to answer in detail instead of being forced into the shape of our first metaphors. A good theory survives contact with strange objects by becoming more precise. A weak theory survives only by ignoring them. Inflated giant exoplanets are powerful because they do not let us ignore them. They are too physically extreme to be folded quietly back into the old image of giant planets. They force the discipline to refine itself, and in doing so, they force us to refine our emotional picture of the cosmos as well. The cosmos is not simply larger than we thought. It is less intuitive than we thought, more conditional than we thought, and in some ways more delicate than we thought. A huge planet can be a world under stress. A giant silhouette can be partly an atmospheric gesture. A category can hold together scientifically while fraying emotionally. These are not the kinds of lessons children's diagrams usually teach, but they are the kinds of lessons mature knowledge keeps bringing us back to, which is why it is worth returning, once more, to that first childhood image of Jupiter. Not to discard it, not to embarrass it, but to place it inside a larger truth. Jupiter is still majestic, still one of the grandest objects in our system, still a giant in every sense that matters locally. Yet after meeting a planet like HAT-P-67b, we can no longer ask Jupiter to carry the whole meaning of bigness alone. The word has split open. Inside it there is now compression, inflation, heat, pressure, escape, time, and the possibility that the most outsized worlds are sometimes the ones closest to the edge of changing into something else. Something else changes once you truly accept that possibility. The universe stops feeling like a gallery of finished objects and starts feeling more like a field of ongoing negotiations. We talk about planets, stars, and brown dwarfs as though they sit still inside their names. But names are only our way of freezing a moving reality long enough to think about it. The objects themselves are always deeper than the label. They cool, contract, migrate, shed, compress, brighten, dim, spin, lock, and evolve. Some do it slowly enough to look eternal. Some reveal the process more openly. Inflated giant planets belong to that second kind of honesty. HAT-P-67b is honest in a very particular way. It tells us that a planet can be measured as enormous and yet understood as tenuous. It tells us that scale can be the visible footprint of pressure rather than the signature of triumph. It tells us that if you want to know what a world really is, you cannot stop at the width of its shadow. You have to ask what maintains that width, what threatens it, and how long those conditions can persist. That sequence of questions is part of what makes astronomy feel so strangely intimate, despite the distances involved. We do not know these worlds by touch, we know them by inference. Yet inference, when it is this careful, can carry emotional texture. A planet in a tight orbit under heavy irradiation begins to feel exposed. A low-density giant begins to feel stretched thin. A brown dwarf packed with mass inside a not much larger radius begins to feel inward, compressed, almost secretive. The physics generates the mood. And mood matters because it changes what kind of memory the viewer takes away. A shallow telling of this subject leaves you with a single impressive line: there is a planet bigger than Jupiter. A deeper telling leaves you with a more durable realization. The largest known giant planets by physical size are not simply more of the same thing. They occupy a different physical and emotional regime. They are worlds where the familiar alliance between size and substance has been broken. That realization lingers because it applies beyond this one object. It changes how you imagine giant planets in general. It even changes how you imagine classification itself. That classification problem is worth staying with a little longer because it reveals how human knowledge matures under pressure. We often behave as if categories come first and observations fit themselves inside. In real science, observations frequently arrive first, and categories have to stretch, split, or sharpen afterward. The planet-star boundary is one example. The planet-brown-dwarf boundary is another. Bodies do not line up and wait for us to assign them neat emotional meanings. They exist under pressure, temperature, mass, and formation history, and our words come later. That is why the edge between giant planet and brown dwarf is not just a technical annoyance. It is a philosophical reminder. A body can be many times Jupiter's mass and still remain around Jupiter's size. Another can be much less massive than Jupiter and yet appear far larger in radius because it is so inflated. Once those possibilities exist, biggest becomes a word that must be handled with discipline. Biggest in mass is one contest. Biggest in physical breadth is another. And the most revealing winners may not be the ones our instincts would have chosen. There is a quiet elegance in that separation. It rescues us from a childish kind of ranking and replaces it with a more adult form of seeing. Instead of imagining one simple summit, we begin to see different ridgelines. Mass has its extremes, radius has its extremes, density has its extremes, irradiation has its extremes, stability has its own story entirely. A planet can rank high in one of those and low in another. A neighbouring substellar object can dominate one metric while barely moving another. The universe becomes less like a podium and more like a terrain of trade-offs. Trade-offs are where reality becomes most interesting. Every gain implies a cost. Every extreme reveals a limit. A very massive substellar body pays for its mass with compression. A highly inflated hot giant pays for its enormous radius with low density and possible vulnerability. A distant cold giant preserves one kind of structure and avoids another kind of stress. Nothing gets everything. The most dramatic worlds are often the ones where the trade-off is easiest to see. That thought brings us back, with more force now, to Jupiter's true role in this story. Jupiter is not diminished by the existence of HAT-P-67b. It is clarified. We now see it as one solution among several. A solution in which gravity and composition produce a giant world of immense mass and substantial radius, without the runaway inflation seen in some close-in exoplanets. Jupiter's size no longer reads as a universal giant planet template. It reads as a local answer to local conditions. That makes it more specific, not less grand. And it makes our own solar system feel more contingent. This matters in the way people do not always notice. When exoplanets first entered public imagination, many presentations treated them as exotic decorations around the real planetary system we already knew. Strange places, yes, but strange in a peripheral way. Over time, the balance flipped. The solar system became one sample among many, and its orderliness, once assumed to be normal, began to look like one style of arrangement rather than the default architecture of worlds. That shift did not make home feel less meaningful. It made it more particular. We live inside one answer among countless alternatives. The same is true of Jupiter. It is our giant, the giant our minds were trained on, the giant that taught generations what planetary excess looked like. But it is only one answer to the problem of how much matter a world can gather, how it can structure itself, and how it can survive around a star. HAT-P-67b is another answer, a more inflated one, a more stressed one, a less intuitive one. A world that reveals not just that bigger planets exist by radius, but that the path to becoming bigger can involve becoming physically thinner, hotter, and perhaps less durable. There is a line hidden in all of this that I think stays with people long after the details fade. A larger world is not always a stronger world. In some cases, it is the opposite. In some cases, expansion is a sign of exposure. A planet can become more visually enormous precisely because its outer layers are being held in a more fragile configuration. That is not the sort of lesson the eye would discover on its own. It has to be earned through measurement and thought. But once earned, it changes how scale feels. Scale becomes tragic in places. Not tragic in a melodramatic sense. Nothing here calls for cosmic sorrow or theatrical language. But there is a sober beauty in recognizing that some of the largest forms in the catalogue may represent conditions under pressure rather than conditions at rest. The inflated giant becomes moving because it is not simply an oversized object. It is a body in a state of tension, perhaps passing through a physically revealing interval in its life under a harsh star. The grandeur remains. So does the instability. And because that instability is not chaos, but law, it teaches one of the most valuable habits in science. Never confuse a striking appearance with an explanation. The radius tells us something real. The density deepens it. The orbit reframes it. The star intensifies it. The possibility of atmospheric escape complicates it. Each layer converts a headline into understanding. That layered conversion is the real pleasure of the subject. Not the first surprise, but the way the surprise remains intact while becoming more disciplined. By now, the title has almost inverted itself. At the beginning, Makes Jupiter Look Small felt like an act of comparison. Here, it begins to feel like an act of revision. Jupiter looks small in one narrow geometric sense next to the most inflated giants, yes. But more importantly, our old idea of what counts as planetary size now looks small. Too simple, too clean, too confident. The geometry was never the deepest correction. The deepest correction is that size, in this part of the universe, is not a straightforward possession. It is a temporary treaty between matter, heat, gravity, and time. And treaties can hold for astonishingly long stretches while still not being permanent. That is one of the strange emotional demands of astronomy. We have to learn to think on timescales that are both immense and unstable, to see 100 million years as significant without treating it as eternal, to understand that a planetary phase can outlast every civilization that will ever exist on Earth and still count as temporary in the life of a system. For a close-in giant planet, that perspective matters. The orbit is short, the heating is relentless, the atmosphere is extended, and every one of those facts implies process. A giant world under these conditions is not simply parked next to a star like a decorative object on a shelf. It is exchanging energy with its environment constantly. Its star is shaping it. The tides are shaping it. Its own gravity is resisting and responding. The atmosphere is not a border in the ordinary sense. It is a region of consequence. You can feel how far this is from the old children's book image of a planet. In those images, planets are tidy spheres under neat lighting, crisp objects with clear surfaces, each one a kind of place. But some of the largest giant exoplanets by radius ask us to imagine something subtler. Not a place with a clear edge, but a body whose outer identity is deeply atmospheric. Not a thing that simply sits there, but a structure whose present state is maintained by active physical conditions. Not a giant because it is packed with extraordinary substance, but a giant because the conditions around it have allowed its outer layers to swell far outward. That is why average density is not a footnote here. It is one of the most powerful translations we have. Radius tells us what the planet's silhouette is like. Mass tells us how much material is really there. Density tells us how strange the relationship between those two has become. It tells us whether the giant shape is backed by giant substance or by giant extension. And for HAT-P-67b, that relationship is so extreme that it becomes difficult to think of the world in ordinary bodily terms. The comparison that keeps suggesting itself is not a heavier and heavier object, but a more and more stretched one. A world whose dimensions have outrun our instinct for what those dimensions should imply. This is where a calmer kind of wonder takes over from the initial shock. The first astonishment was easy. Something bigger than Jupiter exists. The later astonishment is finer grained and more lasting. The laws of planetary structure contain behaviours that our ordinary imagination would never have guessed, and one of the cleanest windows into those behaviours is a world whose physical appearance is almost deceptive in its grandeur. There is no insult in calling a giant planet deceptive here. The deception is ours. We are the ones bringing the wrong instincts to the data. If anything, the planet is being unusually honest. It is telling us exactly what it is through its transit depth, orbital timing, stellar context, mass estimate, and inferred density. It is our language that struggles. Bigger sounds too simple. Larger by radius, but lower in density and much lower in mass than intuition expects, is more accurate but less emotionally efficient. So we begin with the simple word, and then, if we are doing the subject justice, spend the rest of the story repairing it. Repair is a good word. The entire history of science can be described as a series of repairs to language and expectation. The sun does not rise. Earth rotates. Species are not fixed, they evolve. Continents are not anchored, they drift. Atoms are not indivisible. Galaxies are not the whole universe. Planets are not only the sort of worlds found in our own system. Giant planets are not all Jupiter-like in the same way. The largest known giant planets by radius are not simply the heaviest. Each repair makes the world less intuitive and more real. That is one reason this subject stays with people. It is not only about scale, it is about the emotional experience of correction. You enter expecting a larger version of something familiar, and leave having learned that familiarity itself was the misleading part. The giant in your mind was too clean, too settled, too singular. Nature had more than one way to build excess, and some of those ways look almost unstable from the moment we understand them. Even the measurement process carries that emotional charge. Think about what it means that a planet like HAT-P-67b can become one of the strongest examples in this story without ever appearing to us as a simple photograph. We know its scale through the depth of a transit, through the star's response, through careful inference from light and motion. The entire picture is stitched from indirect evidence. Yet the resulting world is not ghost. It becomes, if anything, more impressive because of how much can be known from so little. This is one of the rare places where abstraction deepens intimacy. A tiny dimming in a star becomes an outsized planet. Repeated measurements become a year lasting under 5 days. A wobble becomes a mass estimate. Those numbers combine into density, and density transforms the whole emotional posture of the object. Suddenly the planet is not just huge, it is huge in a way that feels aerated, heated, and vulnerable. The data do not flatten the world into a chart, they restore its physical drama. And once you trust that kind of inference, the larger exoplanet landscape opens differently. We are no longer just finding oddities, we are detecting regimes, regions of possibility, families of worlds whose properties tell us what combinations of mass, distance, heat, and structure can exist. Some of those families are comparatively calm, others are theatres of stress. Inflated hot giants belong to the latter. They occupy a boundary where the architecture of a planet is visibly shaped by being too close, too heated, too exposed for the kind of equilibrium our solar system made us think of as normal. That phrase, too close, is itself a human instinct trying to climb into astrophysics. The planet is exactly where it is, following the orbit that history and physics have given it. Nothing about the system is morally excessive, yet to a mind raised on the spacing of Mercury, Venus, Earth, and Jupiter, the closeness feels almost intimate in the wrong way. A giant world near a bright star seems to be violating a personal boundary. That sensation is useful. It reminds us how deeply our own system trained our expectations. It also helps us feel why irradiation matters so much. At that distance, the star is not background. It is a constant physical presence, pouring energy into the planet's upper layers until the very dimensions of the world reflect the relationship. So the largest planet story becomes inseparable from a star story. It becomes inseparable from orbital architecture. It becomes inseparable from the possibility that present appearance may not equal long-term destiny. In that sense, HAT-P-67b is not just an oversized planet. It is a system event, a body whose known extremity emerges from interaction, not isolation. And that interaction leads to one of the hardest but most rewarding insights in the entire journey. The larger a planet looks, the more careful we sometimes need to be before calling it secure. Some worlds are large because they are compressed reservoirs of enormous substance. Some are large because they are heated into expansion. These are not the same kind of bigness. They do not carry the same implications. They do not even ask to be admired in the same way. One commands the imagination through density and internal power, the other through extension, strain, and law-driven fragility. Both are real, both are majestic, but they teach different lessons. And once those lessons start to separate in the mind, the cosmos as a whole begins to feel more articulate. It is no longer just full of large things. It is full of different reasons for largeness, different kinds of excess, different negotiations between outward appearance and inward structure. That is a richer universe than the one we began with. And it sets up one last deep reversal, because after everything we have said about inflated giants, there is still a lingering temptation to imagine them as the outer edge of planetary weirdness. They are not. They are a visible edge, a dramatic one, but beyond them lies an even subtler frontier, where the problem is not how to imagine a world bigger than Jupiter, but how to imagine one carrying vastly more matter while refusing to grow much at all. That refusal may be the most counterintuitive fact in the entire neighbourhood of giant worlds. We are now so deep into the story of inflation that it is tempting to let bigger dominate the imagination completely. Radius has become dramatic. Silhouette has become deceptive. Heat has become the hidden sculptor. But if we stop there, we miss the other half of the lesson. The universe does not only know how to make giant worlds seem larger than they should be, it also knows how to hide extraordinary mass inside bodies that barely broaden at all. This is where brown dwarfs become impossible to ignore. They matter here not because they steal the title, and not because they can simply be called planets by another name. They matter because they reveal what happens when hydrogen-rich bodies move into a compression-dominated regime so strongly that more matter mostly deepens the interior rather than dramatically enlarging the outside. A brown dwarf can outweigh Jupiter many times over and still remain in the same rough size range. If HAT-P-67b teaches us that appearance can outrun substance, brown dwarfs teach us the complementary truth: substance can outrun appearance. Put those two lessons side by side, and the old intuition finally breaks for good. One world can be physically broader than Jupiter while holding much less mass. Another can hold far more mass than Jupiter while remaining not much larger in radius. The word big was never built to survive this. That is why people who first encounter these facts often feel a kind of mental dizziness. It is not because the science is unclear. It is because the mind keeps trying to rebuild the old ladder while the evidence keeps replacing it with a landscape. We want a simple progression: small planet, bigger planet, giant planet, even bigger giant, brown dwarf, star. But reality refuses the clean visual climb. In one region, more mass barely changes size. In another, less mass under extreme irradiation can produce a remarkably inflated radius. The map bends around physics, not around the ordering habits of our language. And in that bent map, Jupiter looks more and more like a hinge point, not the midpoint of a neat scale, but a body near a natural size plateau for hydrogen-helium worlds. That alone is astonishing. The giant that once seemed like the maximal expression of planetary size now appears as a clue to one of the deeper structural rules in substellar astronomy. Around this scale, the story changes. Add matter and compression grows more important. Remove matter and heavy irradiation can, under the right circumstances, produce bloated worlds with startling physical breadth. Jupiter. No wonder it held our imagination for so long. It was never just large. It was perched near a threshold we had not yet learned to name. Threshold is a useful word here, because it preserves the sense that reality is continuous while our categories are not. A threshold is not a wall. It is a region where behaviour changes. Water warms quietly until it boils. Rock bends under enough heat and pressure that it ceases to behave like brittle stone. Atmospheres deepen into interiors. Planetary bodies gain enough mass that electron pressure begins to matter in ways no everyday object prepares us for. Thresholds are where intuition fails most cleanly, because things remain themselves while beginning to obey a new, dominant logic. That is exactly what happens in the territory surrounding Jupiter: inflated giants and brown dwarfs. The bodies all belong to a broader family of hydrogen-rich objects, yet the governing behavior shifts depending on mass, irradiation, orbital architecture, and internal conditions. This is why the largest known giant planet by radius can coexist in the same conceptual neighborhood as far heavier bodies that are not much broader. Once you really feel that, the phrase, largest planet we've ever found, starts to sound almost modest. It is not that the title is wrong, it is that the title opens into a more demanding reality than titles usually do. We came looking for a giant bigger than Jupiter. We found a world whose size is inseparable from inflation, exposure, and likely stress. We then found that Jupiter itself is sitting near a size limit that makes it more central to planetary physics than casual scale charts ever suggested. And now we find that neighbouring bodies can become vastly more massive without blooming outward in the same way at all. The word largest turns out to be only the first handle on a much larger structure of thought. It reaches into how the universe stores matter. That may sound like too large a statement, but stay with it. When we talk about these worlds, we are really talking about how hydrogen behaves under different combinations of gravity, temperature, and pressure. We are talking about when matter expands, when it compresses, when heat puffs up outer layers, when internal pressure resists further enlargement, when a body approaches stellar behavior, and when it remains below that line. In other words, the story of HAT-P-67b is not merely a curiosity about a distant world. It is one visible expression of a larger truth about matter under conditions Earth almost never provides. And that is why the best astronomy stories never stay where they begin. They open with surprise and end with a revision of what counts as possible. In this case, the revision is profound. A large radius can mean low density. A very high mass can coexist with an almost unchanged radius. Giant planets close to their stars can become inflated beyond what cold system intuition would ever predict. Categories can remain scientifically useful while becoming emotionally unstable. The more carefully we measure, the less the old adjectives can be trusted without context. Context becomes everything. If you tell someone there was a world bigger than Jupiter, they imagine one kind of thing. If you add that it is much less massive than Jupiter, they imagine another. If you add that it is being intensely irradiated in a very tight orbit, another correction follows. If you then explain that the very same physical neighbourhood also includes bodies many times Jupiter's mass that are not proportionally larger at all, the concept of bigness finally fractures into the separate realities it always contained. Width is not weight. Weight is not density. Density is not stability. Stability is not permanence. That sequence of separations is one of the deepest pleasures in learning. It can feel like loss while it happens, because a simpler picture is being dismantled. But what replaces it is not confusion, it is articulation. The world becomes more finely divided, more honest about its forces, more resistant to lazy summary. You lose the comforting diagram and gain the real one. And the real one is beautiful in a harsher way. HAT-P-67b is beautiful because it is swollen, not serene. Jupiter is beautiful because it is massive and structured near a threshold that compression begins to dominate. Brown dwarfs are beautiful because they hide astonishing mass behind an outward modesty that naive intuition would never predict. These are different beauties. None cancel the others. Together they build a more complete emotional physics of giant worlds. By now we have moved very far from the opening image of Jupiter as the unquestioned king of planetary size. But we have also moved toward a better respect for it. Jupiter is no longer just the thing something else surpassed. It is the local giant that helped us discover a plateau, a benchmark that became more meaningful rather than less once stranger worlds were found. That is one of the most satisfying reversals in the story. The comparison does not humiliate the familiar object. It reveals the deeper rule that made the familiar object important all along. And perhaps that is the most human pattern in science. We begin with what we know. We watch it become insufficient. Then, if we are lucky and patient, what once seemed small or simple returns as something newly profound. Jupiter was never merely the largest nearby planet. It was a signpost, pointing toward a whole regime of physics we had not yet explored. HAT-P-67b did not erase that signpost. It showed us where the road keeps going. And the road keeps going because even now, with all these corrections in place, one final emotional problem remains. We understand more clearly what these worlds are doing. We understand the mass-radius paradox better. We understand the role of irradiation better. We understand why size alone cannot rank the substellar universe. But there is still a haunting question underneath all of it. What does it mean that we can know any of this at all? That question matters because knowledge can become so comfortable that we stop noticing how unnatural it really is. We say a planet is 2 times Jupiter's radius, or that it circles its star in under 5 days, or that its density is astonishingly low, and the words begin to sound routine simply because they are grammatically clean. But nothing about the underlying achievement is routine. We are a species that evolved to judge distance by footsteps, weather by skin, danger by sound in the dark, and the weight of objects by lifting them. Yet from a small planet around an ordinary star, using instruments built by finite hands and minds, we have learned to detect the shadows of worlds we will never visit, and reconstruct their physical character with enough precision to discover that some giant planets are swollen almost beyond intuition. There is no way to sit with that honestly and remain completely casual. The strangeness is not only in the planets, it is also in the fact that a nervous, temporary animal can learn to read them. That is part of the emotional afterimage this story should leave behind. Not pride exactly, something quieter. Gratitude, maybe. The kind that arrives when you realize that the universe is not obligated to be legible, and yet, in certain narrow ways, it has allowed itself to be read. A star dims, a spectrum shifts, a wobble repeats. The signal is extracted, cleaned, checked, argued over, revised, compared, and eventually a world enters the human record. Not fully possessed, not exhausted by the data, but known enough that its existence changes the meaning of other worlds. That is an extraordinary sentence to be able to make, and it becomes even more extraordinary when you remember how recent this all is. For almost all of human history, giant planets meant Jupiter and Saturn, plus the dim, icy giants once telescopes and patience brought them in. The Milky Way could have been full of bloated hot giants, compressed brown dwarfs, compact super-Earths, lava worlds, ocean worlds, and we would have walked under the same stars with no practical way to know. Then, within a period so short that it is basically a blink in civilizational time, the silence broke. Planets around other stars were not just possible, they were common, then stranger than expected, then structurally revealing, then numerous enough that the solar system itself had to stop pretending it was a universal template. In that sense, HAT-P-67b is not just a planet. It is also a milestone in human seeing, a marker of how far the method has come, a reminder that our understanding of world has widened enormously without the sky itself seeming to change. That contrast is almost impossible to exhaust. The stars look much as they did to people thousands of years ago. The meanings inside them are now radically different. We sometimes talk about discovery as though it adds decoration to reality, but that is backwards. Discovery strips away the decoration we had mistaken for reality and leaves us with something harsher, cleaner, and more compelling. Before exoplanets, giant planets could still be imagined as a fairly narrow category. After exoplanets, that category became elastic, conditional, and rich with competing physical stories. Before careful mass radius work, largest felt like a straightforward rank. After careful mass radius work, it became a phrase that demands immediate clarification. Before we appreciated inflation and compression as neighbouring truths, it was easier to imagine a universe that arranged giant worlds according to simple visual logic. Now we know better. Better is not always easier. Sometimes it is less comfortable. A simple universe is soothing. A universe where categories blur and outward appearance conceals inward structure asks more of the mind. But it also gives more back. It replaces crude amazement with durable fascination. It lets the title keep paying off even near the end, because the title has become almost reversible now. The largest planet we have found makes Jupiter look small. Yes, but in another sense, it makes Jupiter look newly profound, because Jupiter now appears not merely as a giant, but as a body near a natural structural threshold. And in yet another sense, both worlds make our original idea of planetary scale look small, because the true lesson was never about which sphere won the contest. It was about how badly our first concept of large needed repair. That repair changes the emotional texture of the night itself. You can still look up at Jupiter and feel the old awe. In some ways, the old awe deepens. But it is joined now by an awareness that somewhere out there are worlds whose giant forms are more fragile than their silhouettes suggest. Worlds whose years flash by in a handful of days. Worlds whose atmospheres may be stretched toward escape. Worlds whose dimensions are telling the story of heat and pressure, rather than just accumulation. The sky becomes less like a display of stable objects, and more like an atlas of different solutions to matter. And because matter is the real subject underneath all of this, the story gains a surprising unity. We began with a planet bigger than Jupiter by radius. We moved through inflated atmospheres, stellar irradiation, density, instability, compression, brown dwarfs, thresholds, categories, and measurement. Beneath every one of those topics was the same question: what can hydrogen-rich worlds become under different balances of gravity, temperature, and time? HAT-P-67b is one answer. Jupiter is another. Brown dwarfs are neighbouring answers. The wonder is not that one object broke the rules. The wonder is that there were always more rules than our early picture contained. That realisation leaves a residue that is difficult to fake and impossible to mass produce if it is real. The ordinary word planet no longer feels ordinary. It widens in the mouth. It now contains not only Earth and Jupiter and the familiar arc of our own system, but also these stretched, irradiated, low-density giants whose present shapes may be inseparable from stress and loss. A planet can be serene. A planet can be compressed. A planet can be swollen. A planet can be near a boundary we cannot summarize cleanly. A planet can be a stable home. A planet can be almost all atmosphere in the way it matters to observation. The words survived the expansion of knowledge, but not unchanged. Few words do. And maybe that is the right place to ease the pace a little, because the story has earned its calm. We do not need louder astonishment now. The facts are doing enough on their own. A giant world over twice Jupiter's radius, much less mass than Jupiter, extremely low density, an orbit so tight its year lasts less than a work week. A star bright and hot enough to help swell the planet into a state our solar system never taught us to expect. The possibility that this inflation is tied to an exposed phase, perhaps even one in which atmospheric loss matters strongly. Nearby in concept, though not identical in kind, bodies many times Jupiter's mass that refuse to grow much wider because compression takes over. These are not details around the edges. They are the architecture of the revelation. And the revelation is not just that reality is bigger than we thought, it is that reality is subtler than we thought. The biggest giant planets by radius are not merely oversized, they are physically expressive. They show what happens when heat and gravity do not produce the sort of giant we were expecting. They reveal that a silhouette can be the visible result of tension. They remind us that a record can be temporary, that an object can look monumental while existing in a vulnerable regime, and that the line between intuitive categories is often where the best science begins. We came in through a comparison. Something makes Jupiter look small. We are leaving with a different kind of image now. Not a giant standing beside a larger giant, like monuments in a contest. Something stranger than that. Jupiter on one side, composed and massive near a deep structural threshold. HAT-P-67b on another, swollen outward into one of the most extreme known planetary silhouettes, perhaps held there by a balance that cannot last forever. Beyond them, heavier bodies compressed into similar radii, hiding vast mass behind outward restraint. And above all of it, stars whose light is thin enough to cross immense gulfs and still tell us the shape of things. That is the image that stays. Not that Jupiter was beaten, that the universe was never using our scale in the first place. And once you understand that, even the word scale begins to feel more demanding. We usually treat scale as a matter of simple comparison, one object placed beside another until the eye decides which is larger. But real scale is not just geometry, it is structure, it is density, it is stress. It is what the object is made of, what forces are acting through it, and what kind of future is implied by its current shape. The largest known giant planet by radius forces all of that into the frame at once. It takes the easiest possible claim, this one is bigger than Jupiter, and turns it into one of the best demonstrations that bigger is never enough. That is why the story lingers. It does not resolve into a fact you can file away. It keeps reopening. You can hear that reopening in the questions the planet leaves behind. If a world can swell this far outward, how many similar worlds are we still misjudging because their full context has not yet been measured well enough? If some inflated giants are being observed during especially revealing phases of atmospheric loss or stellar influence, how many of the catalogues we treat as static snapshots are really collections of moving states? If the clean border between planet and neighbouring substellar objects remains partly a matter of formation history and classification choice, how many of our cosmic nouns are more provisional than they sound in ordinary speech? Those questions do not weaken the story. They are the story maturing. There is a false idea that certainty is the only satisfying endpoint of knowledge. In reality, one of the deepest satisfactions comes from seeing uncertainty properly shaped. Not vague, not theatrical, not used as an excuse for speculation, just honest. The radius of HAT-P-67b is astonishingly large by giant planet standards. Its low mass relative to that radius is astonishing. Its density is astonishing. Its close orbit and harsh irradiation matter enormously. Some parts of the inflation mechanism remain active areas of study. Some aspects of its current atmospheric state may reflect a particular moment in the system's evolution. That is not a weakness in the script. It is exactly what the real universe feels like when we are looking carefully enough. Clean where it can be, open where it must be. That balance is part of what separates genuine wonder from cheap exaggeration. Cheap exaggeration only needs the first surprise. Genuine wonder survives contact with detail. It becomes more powerful as the mechanism comes into focus, because the mechanism does not dissolve the strangeness, it gives the strangeness a skeleton. HAT-P-67b is not amazing because it floats free of law. It is amazing because the laws themselves allow something this counterintuitive. A giant planet can become wider than Jupiter by a startling margin, while remaining much lighter. A heavier substellar body can hide behind a similar radius. A star can inflate and possibly erode a nearby giant through relentless exposure. A record can be less like a throne and more like a temporary state written in heat. Those are not decorative facts. They are a more honest mythology for the universe. Not mythology in the sense of fiction, but in the older sense, a structure of meaning built around what kind of world we actually inhabit. The childish mythology says the biggest things are the strongest, and the strongest things are the most stable. The mature one says the cosmos is more exacting than that. Sometimes the grandest silhouettes belong to the most exposed conditions. Sometimes the densest realities hide inside modest dimensions. Sometimes the thing that looks calm is near a threshold you only discover later. And because this is really a story about thresholds, Jupiter keeps returning with more depth each time. It is almost impossible to tell this well without allowing Jupiter to change shape in the mind more than once. At first it is the familiar giant, the unquestioned benchmark. Then it becomes the thing surpassed in radius. Then it becomes the clue that mass and size are not simple partners. Then it becomes a signpost near a natural plateau for hydrogen-rich worlds. By now it becomes something even richer, a reminder that the familiar object was never simple, only familiar. We mistake familiarity for understanding all the time. Jupiter suffered from that. So did the word planet, so did the word big. Familiarity is often the last disguise mystery wears. That line belongs here, because it tells the truth about what happened over the course of this journey. Nothing in the outer solar system changed. No exoplanet grew larger because we learned about it. No star altered itself to fit our updated models. What changed was the comfort of an old image. Jupiter was comfortable. Large, yes, but comfortably large. The giant you could point to. The giant that made sense. HAT-P-67b does not grant that comfort. It asks more from the imagination, because its size cannot be understood apart from inflation, irradiation, low density, and possible loss. It is not the sort of giant that lets you stop at silhouette. That refusal is what makes it so valuable. In a quieter way, it also says something about how science progresses at its best. The most useful objects are not always the prettiest or the closest. They are often the ones that force a correction, the ones that expose the limit of an assumption so clearly that everyone has to refine the framework. Inflated hot giants have done that for planetary science. They have made it impossible to speak lazily about gas giants as though Jupiter were the full script. They have made it impossible to use mass and radius as though one automatically implied the other. They have made it impossible to ignore the role of stellar environment in shaping the dimensions of a world. That is what makes HAT-P-67b feel discovered rather than merely listed. It enters the mind not as a line item, but as a pressure. It keeps pushing on the meaning of size, on the meaning of planet, on the emotional confidence we place in categories, on the assumption that what looks largest must be most substantial. The longer you stay with it, the more it becomes less a record and more a kind of lesson in planetary honesty. And honesty is part of the calm tone this story has been moving toward all along. We do not need cosmic shouting here. Reality is already doing enough. A world over twice Jupiter's radius is already enough. A mass only a fraction of Jupiter's is already enough. A giant orbiting so close to its star that its entire year flashes by in under 5 Earth days is already enough. A density so low that the world's vastness starts to feel like extended atmosphere rather than compact bulk is already enough. The possibility that the same conditions helping create that vastness may also be linked to escape and eventual reduction is already enough. Nothing has to be inflated in the language. The planet has handled that part itself. So where does that leave us now, near the end? Not with a moral exactly. The universe does not hand out morals, but it does offer habits of mind. One of them is this: never assume that a category learned early is complete. Another is this: never trust visual intuition alone in regimes governed by unfamiliar physics. A third may be the most important of all. When a fact seems to reduce reality to a simple headline, stay a little longer. The deeper truth is often waiting just under the headline, and it is usually better than the first version. The first version was that there is a planet that makes Jupiter look small. The deeper version is that the largest giant planets by physical breadth reveal a universe where heat can build enormity without building proportionate mass, where gravity can compress extraordinary weight into familiar widths, where the shape of a world may be the temporary expression of an ongoing struggle, and where our most familiar giant was never dethroned so much as recontextualized. That word matters. Recontextualized. Jupiter is still Jupiter, still immense, still one of the greatest presences in our planetary neighbourhood. But now it lives inside a wider conversation. Its size points to a plateau. HAT-P-67b points to inflation and exposure. Brown dwarfs point to compression and hidden mass. Together they erase the naive ladder and replace it with a terrain of physical regimes. Once you have seen that terrain, you cannot fully return to the old picture. The old picture still works in schoolbook outlines. It no longer satisfies the mind at night. And that may be the right measure of whether a story like this has done its work. Not whether the title was paid off once, but whether the ordinary sky now carries a little more depth than it did before. Whether Jupiter now feels heavier with meaning, not just mass. Whether the word planet has become richer, stranger, and slightly less tame. Whether the largest world we have found by radius now feels less like a bragging point in a cosmic contest and more like a glimpse of what matter can become when gravity, heat, orbit and time lean on it in exactly the right ways. Because that is what we were really looking at all along. Not just a larger planet. A different way for reality to be large. A different way for reality to be large is harder to forget than a simple record. Records can be replaced. Tables can be updated. A new observation can refine a radius, shift a ranking, redraw the edge of a category. But once you have seen that size itself can mean different physical things, that understanding does not really go away. It follows you into every later comparison. Bigger than what? Bigger in which sense? Bigger because of more mass? Or bigger because of inflation? Or bigger because an atmosphere has been pushed outward under conditions that make the whole word giant feel less like a noun and more like a verdict on a temporary state? That is part of why the most careful version of this story remains the most powerful one. We do not need to pretend that one planet has permanently won some eternal title in order for the truth to land. The universe is still being measured. Catalogues will keep changing. Objects will be re-estimated. Borderline cases will keep bothering whatever clean definitions we prefer this decade. None of that weakens the revelation. If anything, it strengthens it, because it reminds us that knowledge here is active, revised, sharpened by better instruments and more patient argument. What matters is not the theatre of a frozen crown. What matters is that, in the world we currently know well enough to describe, a confirmed giant exoplanet exists, whose physical breadth pushes past Jupiter so dramatically that our oldest giant no longer feels like a limit. And even that sentence is only the surface of the correction, because once the mind has absorbed HAT-P-67b properly, it starts to notice an almost hidden humility built into the whole story. We did not discover a larger giant because the universe was trying to impress us. We discovered it because we learned how to stop assuming our own neighborhood was normal. That may be the most adult move science ever makes. It replaces provincial confidence with structured curiosity. It says, our sample was small, our categories were local, our intuition was trained under unusually narrow conditions, and there is no shame in that, as long as we are willing to keep widening the frame. Widening the frame is what turned Jupiter from a final answer into a benchmark. Widening it again turned HAT-P-67b from a curiosity into a clue, and widening it still further revealed a whole surrounding terrain of inflated giants, compressed brown dwarfs, close-in orbits, stellar forcing, atmospheric escape, and size plateaus that no simple chart could have captured at the beginning. You can feel how much richer the cosmos becomes under that pressure. A simpler telling gives you surprise. A fuller telling gives you structure. Structure is what remains after the first shock fades. It is what lets the subject keep living in the mind days later, when the exact numbers have softened and only the deepest lines remain. Jupiter is huge, but not the limit. A planet can be larger by radius while being much lighter. The most expanded worlds may be swollen by heat and exposed by that very expansion. Neighbouring bodies can carry far more mass without becoming much wider at all. Those four truths alone are enough to permanently disorder the old intuition. And maybe that is what real learning feels like at its core. Not addition, but reorganisation. You do not simply stack a new planet on top of the old mental shelf. The shelf itself has to be rebuilt. The meanings of giant, large, dense, massive, stable, and even planet all have to move a little to make room for the facts. That rearrangement can feel subtle while it happens, but afterward, the old arrangement starts to seem almost impossibly naive. Not foolish, just early. Like a first sketch of a landscape before anyone had climbed the hills and realised how much of the terrain was hidden from the flat road below. That image fits this subject because exoplanet science has been a series of climbs. One ridge reveals another. First we learnt there were planets around other stars. Then we learnt many of them did not resemble the solar system's layout. Then we learnt giant planets could live in furnace-close orbits. Then we learnt some of those giants were inflated to astonishing sizes. Then the mass-radius relationship deepened into its own revelation, because more mass did not simply mean more width. Every step corrected the last one without cancelling it. The earlier truths stayed true. They just stopped being complete. That is a very beautiful way for knowledge to grow. It also makes the emotional tone of the ending clearer. The right feeling is not conquest. We are not standing over the universe because we found a bigger giant. We are standing inside a much larger field of intelligibility than our ancestors had access to, and that field is still unfinished. The night is not less mysterious because we can name HAT-P-67b and estimate its radius. It is more mysterious in a disciplined way. Its mysteries now have shape. They have boundaries. They have good questions attached to them. What exactly drives the most extreme inflation in some cases? How atmospheric escape evolves under different stellar histories? How many more worlds near the edge of these regimes are waiting to refine the map? The unknown has become more structured, not smaller. That structure is a gift to tired minds as much as curious ones. It means we do not have to choose between calm and intensity. Reality itself is doing both. The calm comes from lawful behaviour, from the sense that these worlds are not random nightmares or fantasies, but coherent outcomes of physics. The intensity comes from how far those lawful outcomes can drift from anything ordinary life prepared us to imagine. A planet can be stretched into one of the broadest known giant silhouettes, not by becoming overwhelmingly more substantial, but by being heated, expanded, and perhaps exposed. A much heavier neighbouring object can remain stubbornly near Jupiter's size because compression has become the dominant story. Every direction you look, the universe seems to be saying the same thing in different forms. Your first summary will not be enough. And that is why the title has to keep paying off all the way to the last moments. Not because repetition is needed, but because the meaning keeps sharpening. At first, makes Jupiter look small is visual. Then it becomes conceptual. Later it becomes emotional. Jupiter looks small in physical breadth beside the most inflated giants. Our old model of giant planets looks small beside the true range of possibilities. Our language looks small beside the physics it was trying to hold. By now the phrase almost turns inward, toward us. The thing that looks smallest at the end is not Jupiter. It is the confidence with which we once thought we understood what a giant planet was. That is not humiliation. It is perspective. Perspective is one of the few rewards that becomes more soothing as it becomes more extreme. We are not diminished by learning that reality is larger, stranger, and less intuitive than we imagined. We are enlarged by being able to hold that fact without flinching away from it. A species that can detect a subtle dimming in a star and infer from it an overinflated giant world in a 4-day orbit has not conquered the universe, but it has done something very close to miraculous on its own scale. It has extended perception beyond the conditions that produced it. It has taught itself to think in pressures and distances and timescales that the body alone could never inhabit. So the final movement of a story like this has to bring the human frame back in gently, not as a sentimental speech, but as a simple truth. We are small, yes, but small is not the same as excluded. We are not too small to know that Jupiter is near a deeper structural threshold than it first appears. We are not too small to recognise that HAT-P-67b is one of the most inflated giant worlds currently known, and that its enormity may be bound up with physical strain rather than brute supremacy. We are not too small to understand that brown dwarfs complicate every childish ranking of size and weight. We are not too small to let these realizations change the texture of the sky. And once the sky changes texture, ordinary words begin to carry a little more charge. Planet, orbit, giant, year, atmosphere, light. None of them mean quite what they did at the start. They have been deepened by comparison, by correction, by the pressure of reality against language. That deepening is, in its own quiet way, the whole point of long attention. To stay with something until the obvious version gives way. To keep listening until the fact stops sounding like a headline and starts sounding like a world. Which is what HAT-P-67b became for us over this journey. Not a statistic, not a thumbnail, not a bragging point in a cosmic list. A world. A very strange one. A giant that widened the meaning of giant. A record that exposed the limits of the word record. A far-off body whose shadow crossing a star was enough to teach us that some of the largest planets by radius are not monuments of pure mass, but inflated, irradiated, low-density worlds living under conditions our own solar system never taught us to expect. And once you have learned that, there is really only one thing left to do with Jupiter. Look at it again. Look at it again, and it is still magnificent. The bands are still there. The storms are still there. The mass is still there. Pulling on moons, shaping trajectories, holding itself in that immense, compressed grandeur that made it the king of our childhood imagination. Nothing has been taken from it. If anything, more has been given. Jupiter no longer has to carry the burden of being the final form of planetary excess. It can be what it truly is, one of the great local answers, a giant balanced near a profound structural threshold, a familiar world that became even more interesting once stranger worlds were found. That may be the most satisfying kind of revision science offers. The old object survives. The old awe survives. What changes is the depth behind them. Now, when Jupiter comes into view, it does not stand alone in the mind. It stands inside a wider universe of giant possibilities. Somewhere out there are worlds so inflated that their radii push far beyond Jupiter's, not because they are proportionally more massive, but because heat, orbit, and atmospheric structure have stretched them into enormous silhouettes. Somewhere out there are neighbouring substellar bodies carrying many times Jupiter's mass, while refusing to become dramatically wider, because compression has taken hold with a force no everyday experience can prepare you for. Somewhere out there are systems where the shape of a world may be telling the story of a temporary state, a giant body swollen under stellar assault, perhaps even slowly losing the very layers that make it look so immense. And all of that now belongs to the meaning of the word planet. Not neatly, not finally, but truly. The deepest payoff of this journey was never just the comparison. It was the realization that a planet can become enormous in more than one way, and that those ways do not carry the same consequences. A larger radius can mean lower density. A greater mass can leave radius almost unchanged. A giant silhouette can be a sign of strain rather than simple dominance. A world can be broad because it is full, or broad because it is swollen. Those differences are not technical footnotes. They are the actual texture of reality. They are what turn astronomy from a list of spectacular objects into a discipline of seeing. And seeing is the right final word to stay near. Because what changed over the course of this story was not the sky. It was our way of seeing the sky. The familiar giant became a benchmark. The record holder became a lesson in inflation and fragility. The neighbouring brown-dwarf regime became a lesson in hidden mass and compression. The old ladder of bigger and bigger worlds dissolved into a terrain of thresholds, plateaus, and competing physical pressures. The universe did not become more theatrical. It became more articulate. That is why the title keeps echoing after the facts settle down. The largest planet we've ever found makes Jupiter look small. Yes, but by the end, the phrase no longer lands as a boast about cosmic size. It lands as a correction to human intuition. Jupiter looks small in one specific geometric way beside the most inflated known giants. More importantly, our old concept of what giant planets are supposed to be now looks small beside the truth. The surprise was never only that there exists a world over twice Jupiter's radius. The surprise was that such a world could be lighter than intuition expects, thinner in substance than its scale suggests, more exposed than its grandeur implies, and perhaps caught in a condition that will not last forever. That is a very different kind of largeness. It is not the largeness of a mountain. It is not the largeness of a fortress. It is the largeness of a world expanded under pressure, a world whose vastness is inseparable from heat, orbit, and the laws that allow gas to become architecture on a planetary scale. Once you feel that, the image that stays is no longer one of two giant balls lined up side by side in a contest. It is subtler than that. Jupiter, dense with meaning, holding near a deep threshold, HAT-P-67b, widened into one of the broadest known giant silhouettes, its dimensions telling a story of irradiation, low density, and physical tension. Beyond them, heavier bodies compressed into outward modesty. Above them, stars whose light crosses impossible distances and still gives up enough information for us to know that these worlds are there. That image lingers because it contains two truths at once. We are small, and we are astonishingly well placed to witness. Not to witness everything, not to master the universe, not to close every question, but to know enough for the ordinary to stop feeling ordinary, enough for Jupiter to become strange again, enough for the word planet to widen, enough for a tiny dimming in a distant star to become a world so large by radius that it reorders the imagination, and then, if we keep listening, reorders the imagination again by showing that size was only the beginning of the story. Maybe that is the quiet gift hidden in all great astronomical discoveries. They do not merely tell us that there is more out there. They teach us how much of our own certainty was built from a narrow sample and how beautiful it is to outgrow that narrowness. They turn confidence into curiosity without turning wonder into noise. They let reality remain calm while becoming far more extreme than we had guessed. So the next time Jupiter rises, it may look the same as it always did. A bright, wandering presence. Striped, massive, serene from a distance. But if this journey has done its work, it will not feel quite the same. You will know that somewhere in the dark there are giant. Worlds wider by far, worlds less dense than your instincts allow. Worlds heated until their atmospheres swell into almost implausible breadth. Worlds perhaps already part way into losing what made them famous. You will know that beyond them lie heavier bodies that hide astonishing mass inside similar sizes. You will know that largest is never just one thing. You will know that the sky above us is not arranged according to the comfort of our first metaphors, and Jupiter, still beautiful, will seem not smaller in dignity, but deeper in context. That is the final change. The giant we thought was the end of the scale was really the beginning of a more difficult kind of seeing. And once you have learned to see that way, the universe does not get simpler again. It gets truer. Jupiter remains. The larger worlds remain. The light keeps crossing the dark. And for one brief span of conscious life, on one small planet, we are here to notice that reality can build a world so vast that it makes Jupiter look small. And even then, that is still not the strangest part.